This is shear failure in shallow foundations. In the early 20th century, Karl Tarzaghi identified three distinct types of failure in shallow foundations: general shear failure, local shear failure, and punching shear failure. But why is this so important? By analyzing these types of soil failure, Terzaghi developed a method for determining the bearing capacity of soil, a crucial factor in foundation design. Soil is one of the most complex materials engineers encounter, largely due to its unpredictability. Karl Tarzaghi's work revealed that for a continuous, shallow foundation placed on compacted soil, we can divide the soil beneath the foundation into the following zones. A triangular zone, ACD, directly under the foundation. Radial shear zones, ADF and CDE, with the curves DE and DF forming arcs of a logarithmic spiral. Two triangular Rankine passive zones, AFH and CEG. Additionally, the soil above the pile depth can be ignored and replaced with a uniform load, as shown. To understand how Terzaghi derived the bearing capacity for such a footing, let's focus on the first triangular zone, ACD, directly under the footing. We will need to solve for the equilibrium of forces in this zone. The forces exerted between the footing and the soil must be resisted by the friction in zones AD and DC. You might notice there's a lot of information in this diagram. I recommend pausing the video here to carefully examine how the footing achieves equilibrium. To make it easier to understand, let's break the forces down into three main components: the force exerted by the weight of the soil, the force exerted by the cohesion of the soil, which refers to friction between the particles, the force exerted due to the surcharge. For the footing to be stable, the total forces resisting the load must equal the applied forces. In other words, the forces in red, resisting, must balance the forces in blue, applied. Let's begin by looking at the first component, the soil weight distribution. This forms a triangular shape, as shown in the diagram. Next, we'll determine the resultant force of this distribution. For a triangular load, the resultant force acts 1/3 of the way from the base. That's measured from the wider end of the triangle. To calculate the magnitude of this force, we start by finding the area of the triangular load. This is equal to 1/2 of the pressure at point D, which is the depth at that point, multiplied by the unit weight of the soil, and then multiplied by the base of the triangle. Since the depth and the height of the triangle are the same in this case, the expression becomes proportional to the square of the depth. This gives us the total resultant force, as shown in the figure. Now, looking at the surcharge distribution, we can see it forms a rectangular load shape due to its uniform nature. This results in the following pressure diagram. In this case, the resultant force is directly related to the magnitude of the surcharge and the depth at point D. Similarly, the cohesion diagram follows the same shape, but here it's scaled by the cohesion value multiplied by the height at point D. Now, by combining all these values, we arrive at the following equilibrium equation. You'll notice that for each of these resultant forces, there are factors, coefficients that depend on the friction angle of the soil. This angle varies depending on the type of soil. For instance, if you're dealing with clay, the friction angle might be as low as 10 degrees, resulting in lower factor values, which indicates the soil is more susceptible to shear deformation. On the other hand, gravel can have a friction angle of up to 45 degrees, leading to larger factor values and making it much better suited for shear loading. Can you think of other positive qualities that gravel brings to the table for foundation design? Leave your comments and questions below.